Hello. Hello, can you hear me? Hello.
Yes, sir.
Yes. So yeah, I think we will start this class maybe after 4 or 5 minutes when these two or some of your other friends come. But before that, if you have any questions, doubts, the next week is the exam. So I'm sure you guys have a lot of questions and doubts. So feel free to ask them now.
Sir, what will be the syllabus?
So syllabus will be till MST. Okay, so basically it will have contain the concepts of the sorting, searching, and basic graph algorithms, BFS, DFS, and their applications, and this minimum spanning tree, and all of them. But it's important to know that what we will be asking questions will not be like, oh, apply this MST algorithm and we'll get it, or what is the write down the pseudocode of this the Prim's algorithm or something like that. Such questions will not come. So instead, what will come is that there will be some questions to solve some problems. Either you have to use some properties of the MST or some particular MST or BFS or DFS or sorting algorithms to solve it. So that means it's kind of reduce the problem to, I mean, kind of using one of the standard algorithms to solve some other algorithm, or some other. I'll ask you to design some algorithms whose basic idea of the algorithm or basic principle of the algorithm would be something that you have seen in one of those algorithms. So just memorizing these algorithms will not do. So of course you have to understand all these algorithms, because these algorithms are the basics of this stuff. So all these algorithms that we have done so far, so basically what all things have we done? Let's quickly maybe revisit in some sense. We have what we have done so far. Oh, sorry, I have not shared my screen. Okay, what have we done so far? So what we have done so far is basic things like binary search. Now, binary search is of course a very powerful tool using which lots of other problems can be solved. You have seen it in your problem sets and in your assignments also. We have seen sorting, and we have seen things like kind of, you can think of this greedy sorting kind of stuff like that. Something like bubble sort or selection sort, bubble sort or selection sort. You have seen the these recursive algorithms like merge sort or quick sort, and you have seen some kind of a data structure based algorithms basically you have seen heap sort, and you have seen some non comparison sorts. So sorting that doesn't involve comparisons, something like the bucket sort, or counting sort. Now, other than that, you have also seen some lower bounds of sorting. Now, all of these concepts you have to go. So you should go over all these algorithms. Okay, all of them individually, and don't try to memorize them, but instead try to understand what all things are being done. For example, when you are dealing with heaps, you should kind of know what the heap structure is doing, what are the why is it correct, why is it what is it what is the time complexity of various stuff, and so on, right? Similarly, the merge sort, the concept of trying to use recursive algorithms there. So that one you should try, understand that. And similarly, this lower bound, all of them, try to understand these algorithms rather than memorizing them. Memorizing them will not take you anywhere. Okay, so as I've already told you a million times, you have these three parts of any kind of algorithm. So design of algorithms. So what is the main idea and how you are going to design that algorithm? You have the proof of correctness. Now, sometimes in many settings, the proof of correctness can be obvious from the design of algorithm. Sometimes it might not be. And sometimes this goes hand in hand. And the other one is the time complexity, or in the time complexity or space complexity. Yes, space complexity. We have mostly done with that is most probably what space complexity as such in this exam. So how you can design an algorithm, this is something that you need to do. How you can prove the correctness of the algorithm, and how you can prove the time complexity of this algorithm. So not only for this setting, but for the other stuffs also. So other than these things, we have done some basic graph algorithms. So by basic graph algorithms, we started with something like just this, the representation of graphs. I mean, this is not a part of graph algorithm, but somewhat related to it. So, and that's just symmetrics. Then you had BFS and DFS. Now this is very important. Okay, now BFS and DFS are two traversal algorithms.
Sir, your voice is breaking.
Particularly in the topological sort. Sorry?
Your voice was breaking.
Hello?
When discussing the
Can you hear me?
earlier part. Hello, am I audible?
Sir, your voice is breaking.
Oh, so from when?
From the graph algorithm.
From when is my voice breaking?
Sir, when you were saying about DFS.
Okay, when I was saying about DFS and BFS. Okay, is it better now? Is it clear now? Is it clear
Sir.
now?
Yes, sir. Yes, sir.
Okay, excellent. Yeah. So, not only, so what I was saying was that not only this BFS and DFS, not only are they traversal algorithms, right? They are also applications. They have lots of applications. For example, finding connectivity, finding the shortest path, finding this topological sort, and many of the other structures, right? So it's not just coming up with understanding the BFS and DFS, but also these properties of BFS and DFS trees. And this is something that you should understand. So not only you should understand what the algorithm is doing, how the algorithm is evolving, but also what it can do or what are the structures. Now, in the problem sets that has been given to you guys, quite a lot of these things have been covered. Okay, so please go over the problem sets. Hello, is the connection fine now? If I saw it.
Yes, sir, you are audible.
Okay. And other than that, there is also the minimum spanning tree. Okay, so we have done the two algorithms. I will kind of go over a little bit of them both today. Again, if you have, particularly if you have any doubts, the Kruskal's and Prims. So both of them are algorithms for which the proof of correctness is a bit more non-trivial than what you have seen so far. Okay. Now, so did you guys follow the Prim's algorithm that was discussed in last class? Since no answer, I'm assuming that you have understood it perfectly, right?
Hello, sir. I got disconnected in between. Just got to
Okay.
hear the last part. Can you repeat this once?
I know that you have understood the Prim's algorithm that was discussed in last class.
Sir, I understood the Prim's algorithm and like generally the proof of correctness, but like in the proof of correctness I did not understand thoroughly, so I did not have the time to study in between. So I think if we can go over that in
Okay.
brief.
So you are the only person who did not understand. Rest of your friends have understood. They are not answering anything. There seems to okay. So no problem. So so in that case, Debashri, you right?
Yes, sir.
Debashri, Devarshi.
Devorshi.
Yeah. So maybe it will be better that if you can visit my office and we can discuss it in more thorough details. I will explain you perfectly. Because rest of your batchmates seems to be completely understood it. Well, they're not even answering any questions.
Okay, sir. I can
Right.
visit
So
after the
Prince and
tutorial
Kruskals
to
is
make that. Okay.
no, I am not there in the class. So can you come tomorrow? Tomorrow,
Yes,
day
sir.
after tomorrow, anytime?
Yes, sir. Yes. Sir.
Yeah, then we can discuss that in that time.
Okay.
So, okay, so let me ask a few questions. And Binit Jha, Binit Jha, are you there? Binit Jha is not been there. Okay. Dhananjay Sarkar, are you there? Dhananjay Sarkar is also not there. What's going on? Oh, Binit, can you give me an example of a graph, or can you draw an example? I guess that you don't have a microphone or something like that, maybe. Can you produce an example of a graph where the Kruskal's algorithm and the Prim's algorithm gives different spanning tree? Soham Das?
Yes, sir.
Yeah, do you have one such example?
Sir, in
Did
Prim's
you understand?
algorithm,
So you are
Sir.
in MTech CS, right?
MTech CRS, sir.
You are in MTech CRS. Okay, you understood Prim's algorithm fully, right? In and out.
Yes, sir. I understood the algorithm.
Okay. So can you just produce me that one such example graph?
Actually, in Prim's algorithm, we can select the first node. Any vertex can we select. So
So
if we select some vertex whose edge weight is larger, then I think we can.
what do you mean a vertex with edge weight? Can you be a bit more clear? What do you mean vertex weight is larger?
No. I mean that edges which are incident with that vertex.
Okay. Is larger than what? Is larger than what?
We can choose the largest weight. No. Sorry, sir.
No, think about it. Think a little bit more on it carefully. Okay. Think a little bit more, and then I will come back. And if you have some ideas,
Okay, sir.
Shubhimoy Hatai, are you there?
Yes, sir.
Shubhimon, yeah. Do you have any idea? Can you give some how will you answer this question if I ask you that that can you construct or is there a graph for which the Prim's algorithm and the Kruskal algorithm will give different spanning tree? Shubhimon, I understand that you don't understand these things, but at least keep yourself unmuted and try to answer what I'm saying.
Sir.
This is a bit rude when I am asking something and you guys just completely shut off and all. What happened? You have some ideas? Can you say yes, no?
No,
I don't
sir.
understand. I understand something. Tell something.
No, sir. No, sir.
What is no?
Sir,
What do you
I
mean?
understand it's Kruskal algorithm.
Okay,
Means
but what
Prim's
about Prim's
algorithm? I see that one vertex we are traversing one vertex more than one time. So
You are traversing.
this is
What
the
you're talking
crucial
about?
difference from
What is the goal of the Prim's algorithm? What is the goal of the Prim's algorithm? Can you tell me?
goals. It is finding minimum spanning tree.
Okay, very good. And what do you mean traversing this?
And we are
this thing?
finding the
Traversing,
minimum distance.
Hmm. Yeah. Okay. I mean, so okay. Let me ask you. I mean, I am assuming that all of you are trying. What I am asking you. I got a message. Okay, beneath you're writing some statements. Maybe you should finish this whole sentence. I can only see half of it. Anybody has some idea? Is it possible? Not possible? Something? Can somebody say this thing?
Sir,
Is
we
it?
can
Yeah.
Hello?
Okay, one by one, just one second. So who started talking first? I think Rachit Parikh started, right? Rachit,
Yes,
are you-
sir.
Yeah. Why don't you?
Maybe when we have, let's say, one vertex is there, A, and it's connected to B and C, and the edge weight is the same. Maybe then we can have, like, I'm not sure, but just a guess.
Sir, what I am saying, if we start a triangle,
Hmm.
then if all the edge weights are same,
Hmm.
then in Kruskal's algorithm, first it will look for A to B or A to C, wherever it is go. But I don't think in Kruskal's algorithm, if you go from A to B, then it will look for the edges from B. But in Prim's algorithm, it will look for edges from B as well as edges from A also.
We
Hold
can
on.
connect graph G to
Kruskal's
B.
algorithm, you don't travel,
In
you don't go by vertex, right? In Kruskal's algorithm, you will pick the smallest edge, which might be this,
Yes.
and then you pick another smallest edge, the next smallest edge, which can be anything, either of this or this. It depends upon.
Which can be so. Yeah. In
Sir, the difference is in Prim's algorithm, all the intermediate steps, in all intermediate steps, the graph should be connected.
Right. That is true. You're very correct. In the Prim's algorithm, in all the intermediate steps, the graph is connected. That is not true for the Kruskal's algorithm. But that doesn't answer my question, which is that
Sir,
can is there a graph for which two different, I mean, if you run Prim's algorithm and if you run Kruskal's algorithm, two different trees will be formed.
So, sir, one example that I can initially think of that would not always provide a different graph, but sometimes if there is a triangle and all the edges are same, then like both the algorithms can select two of those three edges, and that can be different, but like it is not dependent on the algorithm, so to say.
Okay, so you are right that if you have a triangle, yeah, somebody wants to
Any
answer.
two of those three edges can be selected, and that is in some sense the sorting dependent.
Right. So it depends upon, so the Prims might choose this and this, whereas maybe sorry, Kruskal's might choose this and this, and Prims might first choose this and then end up choosing this. But that is
Yes.
because of the ordering of the edges, right? All of them have same weight. What is the ordering? There can have multiple ordering of them, right?
Yes.
Okay, so first of all, this so we all come down to the fact that it's all depend on the ordering. Yes.
Sir, is it that all possible MSTs we can get using Prim's algorithm or Kruskal's algorithm? I mean, any one of these algorithm gives all MSTs by some way.
Yeah. So good question. Very good question. Very good question. Yeah. So that is another way of asking this one. Is it possible that so there can be a number of MSTs, right? Is it possible that the Prim's algorithm can give any of the MST, or Kruskal's algorithm can give any of the MST, depending on the ordering of the vertices or the edges, edge weights? So let's start with a slightly different question. And these are the questions that you should ask yourself also when you are reading this kind of stuff. Okay? What happens if all the edge weights are different? Then what happens? Let's start with a very simple thing. So because all of the examples that you are trying to create are things like this, right? What happens if all the edge weights are different? Then what happens? In that case,
unique.
Then the MST would consist of the n minus, like, no, not always.
somebody told tree is unique. Can you prove it?
Unique,
Why?
sir, it will be the same.
Yes, sir, unique. That is in that case.
Yes. Why?
Because
Okay. Hold on. No, I'm sure you have some idea. So let me ask all of your friends. I will give you a couple of minutes or maybe 5 minutes. Okay. Prove this one. So this proof is a typical example of using the same set of arguments that we have used for Prim's and Kruskal's, but prove it that using those things that if all the edge weights of the tree are distinct, then there exists an unique MST. Okay, so if
sir, can you repeat the question, please?
yes, I'm writing it. Yeah. Is the question clear?
Sir,
Hmm?
in Prim's algorithm, it is clear. Using Prim's
No,
algorithm.
no, hold on. This question is nothing to do with Prims or Kruskal's. This is about the
Okay.
whole graph. Okay, I'm not saying that whether Prim's algorithm will produce a unique MST or not. I'm saying that the whole graph itself has only one MST.
Yes, sir, because the permutation is unique.
It's just even the
Because-
permutation is unique.
Yes.
So
For increasing order, we can there is only one permutation.
yes, yes.
So
Sir,
there exists a unique MST.
if there are two
Why
MST.
I don't see that jump.
Sir, if there are two MST.
Hold on. Who is saying Venkatesh? You are going in the right direction. Yes, just hold your thoughts. Yes, you're going in the right direction. Your arguments are right. But somebody told about this or permutations. Even if you say that the permutation is unique, which is correct, at best you can prove that Kruskal's algorithm will produce a single MST, a unique MST. Why will there? But that doesn't mean that there doesn't exist any MST. Kruskal's algorithm is a way to produce one MST. But what is the guarantee that there is no other MST? Who was it that was asking this one? Siddharth,
sir.
I think, right?
Yes, sir. Yes, sir.
Siddharth, yeah. Do you understand this thing?
Yes, sir. Yes, sir. You are right.
We are not asking about one particular. So this is in fact not a algorithms question at all. This is a graph theory question almost, for that matter. Yeah, somebody has raised hand. Who is Devorshi? You have got the solution. That's what you mean, right?
Yes, sir.
Devorshi? Okay,
Yes, sir.
very good. Bishwajit Mondal? Bishwajit Mondal, are you there? Pradeep Das, are you there?
Yes, sir.
Yeah. So I mean, so you are from
Hello.
MTech CS or MTech CRS? Pradeep, are you from
MTech
MTech?
CS.
MTech CS. So do you have any?
Yes,
Did you manage to get a proof of this statement?
Sir, first to it is two distinct MSP, let's say T1 and T2.
Okay. Excellent. You have got in the right direction. If you have said this statement, I understand that you have got in the right
And
thing.
then the minimum age weight both these T. Let's say E1 be the minimum age weight in T1 and E2 be the minimum age weight in T2.
Exactly. Very good. So let T1 and T2 be 2 MST. Okay. Now we can order the edges, right? Order the edges of T1 by weight. Let this be E11, E12 till E1n minus 1.
Yes.
And similarly for T2. So this, let's say E21, E22 till E2n minus 1. Now
Yes.
find the smallest I such that E1i is not equals to E2i. So that means if this is the E1i and this is E2i, it means everything before that, so this one and this one, they are identically same. So this is the place where they are different. Okay. So now that means what we say is that without loss of generality, okay, so we don't know which one is bigger. So basically it's the two cases. So but since we don't want to deal with two different cases, we can say that, let's say that the first one is bigger. So this is what we say when we don't want to deal with both the cases separately. Right? So in that case, so that means this first one is big. So consider T2, sorry, consider T1 union E2I. So what does this tree has? Let's see. So this tree has edges E11, E12 till E1I, and then it also has E2I and some other edges like this. Right? Because now, I mean, now that I have added this one, so I should add this E2I using a different color. Right? Now, that means that this graph, so there exists a cycle.
Sir, are you writing it in ascending
In
order? Or
T1,
descending order?
I'm writing it in ascending order. Okay, so these are all small.
So E2I will be
Sir, if
before
you are
E1I.
writing in,
Oh yes, E2I will be before, right? You're completely right.
yes, that was.
Yes. E yeah. E2I, and then E1I is there, right? Now let's look at it. What is it? It's a EI minus 1. Now, can there be a cycle containing in this set using this set? So I know that there exists a cycle in this, but can that cycle? So that cycle, of course, contain cycle. Let's call this one. Let the cycle be C. Let C be the cycle. Of course, C must contain E2I because I have added the E2I and that has produced cycle. But can there edge from this set? What do you think? Can there be an edge in that cycle from this set?
Sir, I is the least position where there is a difference, right?
Right.
Then all the before edges are in T1 and T2 both. Both have those edges.
They are in T1, T2, right?
Yeah. So if they makes a cycle, then in T2 there will be a cycle.
Right. So since
The first part is present in T2.
Yeah.
First part is present in T2 also.
First part is present in T2 also, right? Since this one is in T2, therefore, so there cannot be a cycle, be a cycle comprising of only edges in this set, right? Let's call this one E prime in E prime. So that means there must be, there exists a J, which J is bigger than I, or bigger than or equal to I. So that means in this set, such that E1J is in C. So in this cycle, there is of course E2I, and there is another edge which is bigger. And since E1J is bigger than E1, bigger than or equal to E1I, right? I mean, in fact, it's strictly bigger because we have assumed that they are all
There
distinct, they
cannot be
anything
equality.
different. Oh, there can be an equality. Sorry, if it's the equality if j equals to I. Sorry, but this is bigger than E2I strictly, right? So T, which one was it? T1, right? T1, yes. T1 union E2I minus E1J. So I've produced a cycle, removed an edge from the cycle, is a tree with weight less than T1, right? Because I've added something bigger and removed some, so this is something smaller, remove something even bigger, and which is a contradiction. Contradiction, as T1 was a MST. Correct. Any doubts? Hello.
Hello,
Sir,
sir.
I had a, like, not regarding the proof, but like, if there can be an extended statement for this,
Yes.
can I ask that?
Yeah,
So
yeah, go ahead.
when we are discussing the initial preliminaries before the Kruskal's algorithm, we showed that if an cycle contains the minimum weight edge can only not be present in a MST if there is a cycle containing all the edge weights being the minimum edge weight.
Right.
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 So from that, can I extend this statement to if all the cycles in a graph contain distinct weights, then the MST is going to be unique? Because essentially what we are
Yes,
doing
of course,
is that,
of course. If all the cycles in a graph which has distinct edge weights, then also you can prove that same thing. Yes.
and another thing I'm not sure about, if like all the edge, like if no cycle in the graph contains all all the same edge weights, can you show us an example? Suppose a cycle has got 2 repetitions, but it is a 5-length cycle. Whether there can be 2 different MSTs from there, I cannot construct at least.
I mean, 2 different MSTs from 5-length
cycles which have some distinct edge weights, some same edge weights.
Good, very good. It cannot have. Can it have? Think of it.
That's what I was thinking, that if the cycle does not have all the same edge weights, the spanning tree would always just eliminate the highest value edge weight.
Yes,
from
it cannot
the
have.
cycle.
So if you take a, I mean, in this case, right, when you have added a cycle back, when you added something smaller, right?
Yes.
The only option is that all the other edges are of same weight.
Yes, that's what I'm saying. So that would be a stronger statement than this, right?
That is a stronger statement than this. You're completely right.
Okay.
Okay, in fact, you can say something more, okay? So say let the graph, the edge weights are all edge weights are all integers, just to make our life simple. Okay,
Sir,
yeah.
sir, can you write the statement that Devosi said? I don't get that statement properly.
So one statement that he told is that if in a graph all the cycles have distinct edge weights, then the graph has a unique MST. Okay.
All the cycles means the sum of the edges contained in that cycle, right?
No. I mean, like for example, this cycle. Okay, let's think of this particular thing. I mean, this is a graph. I'm drawing a graph. Hold on. Say 1, 1, 1, 2, 2. But this is 3, 4, 5, 6, 7. Now, in this graph, you cannot say that all the edges are of same are distinct weights, right? They're edges of same weight, some of them, right? Like this edge and this edge are of same weight. This edge and this edge is the same weight. This edge and this edge is the same weight.
Okay. Now I
But
understand.
in this graph, this cycle, there's only one cycle, and that has all distinct weights. Okay. Now you can have more cycles. Maybe there is cycles like this also. Okay. And that also has a weight 8. Okay. It has multiple cycles, but all these cycles have distinct edges. In that case, also you can think as a unique.
Sir, your voice is breaking. Can you repeat, sir?
Yeah. So in this graph, right, all the edges that form part of some cycle. So all the cycles have distinct. Okay, although there are same edge weights across this thing, right?
Yes.
So what happens is that it's this cycle that we form, the fact that all the things are distinct. Can you tell me where did you form that all the things are distinct? Yeah, maybe this is a good point. In this proof, I can go over the proof. I mean, not go over, but I can slowly show you the proof. Where did we use the fact that all the edge weights are distinct?
So to make this strict inequality between E1i and E2i.
We can make this strict inequality, right? So here we know that we can say the smallest I such that these two are not equal. So this is saying that, what does this say? Actually, what I've written here is slightly wrong. So this is saying that these two edges are distinct, right? The edges are not same. What I meant here is that the weight of the edge is strictly more than the weight of the edge. And this is something that we can say because the edge weights are distinct. Okay. Now, okay, so this is the place where I've used the fact that the edge weights are distinct. Because if the edge weights are not distinct, then it can be that these two edges are not same, but the edges are same, the weights are same. And then I cannot give a strict inequality. Now, where have we used the strict inequality? Let's see. Where have we used the strict inequality in the proof? We have used it, if you go down slowly, we have used it only over here. When we are adding this edge and removing it and trying to prove that, see, I have got an edge weight strictly less than this. Right? So I have added an edge back, created a cycle, and then removed an edge whose edge weight is, otherwise I would have got it greater than or equal to or something, right? If I did not have this, if I did not have, maybe I could use a different color, what is it, say maybe green. If I did not have this strict inequality, I would have got greater than or equal to, and in that case, here I would have got this is greater than or equal to, and in that case I would not have produced, this would not have been exactly tight. I mean, not strict, which you could not have argued afterwards. So all that mattered was that in that cycle, I have added an edge and removed another edge of weight strictly bigger than what I've added. And that is helping to get the contradiction, right? But it is all we are doing is within a cycle. So if you can say, oh, see, this one and this one are part of a cycle, and in a cycle, I know all the edge weights are distinct. So these two cannot be equal. These two must be strict, this inequality. Then also we are done. Right?
Yes, sir.
Is this clear?
Yes, sir.
So using the same argument, you can prove that for this graph also there exists a unique MST because in any cycle all the edge weights are distinct. So if I have to write down this statement very fully, if in a graph G all edges that, or maybe forget all of it, all cycles has distinct, or maybe this is not right. In a graph G, if any cycle in G has distinct edge weights, oh God, what am I writing? Then the graph has a unique fine. Hello. Okay. So this
Yes,
is
sir.
basically what you can prove. You can prove something more than this also. Okay, and this will help think about it. I'm not going to tell you. Think a little bit more about it. I can use some words. If you want, you can come back to me or to the TS and ask. Any two MST are same. Frequency of edge weights in any two MST now. What do I mean by frequency? What do I mean by those things? You will be able to think about it later. Okay, and using that you will slowly start understanding whether the Kruskal's algorithm or Prim's algorithm can produce any MST or not, depending on the ordering. Okay. Okay, so what I will do now is that one thing that has not been done very carefully is the understanding of the time complexity, because it was rushed even when I explained it, and possibly it was not done completely in the next class also. So let me quickly go over this runtime of these algorithms. Now, okay, so of course we know this algorithm, so the MST, and we're talking about finding MST, right? And here is the Kruskal's algorithm, which basically says that, okay, you pick a minimum weightage, right? And if that minimum edge weight is possible, meaning if it doesn't create a cycle, then you pick it and go to the next step. So here is the simple pseudocode. sort the edges in an ascending order by weight. Now for every edge in the according to the ordering, you pick that edge which is a UV. If adding the edge UV don't create a cycle, then you add it, and else you move to the next. So any doubts about this particular Kruskal's algorithm? Okay. So if not, then can you tell me what is the runtime of this algorithm? Kuntal, are you there?
Sir, your voice was breaking again, I think. Can you tell me afterwards?
Oh,
was not audible?
From when was it not audible? Can you just tell me?
After, can you tell me?
Oh, can you?
What's the question?
Can you tell me the runtime of this algorithm? Can you tell me the runtime? What is the time complexity of the algorithm? Hello, is it clear?
Yes, sir.
Kuntal, did you understand the statement?
Yes, sir, yes, sir.
Yeah. Can you have some idea about this one? So Kuntal, you are from MTech CS or MTech CRS?
MTech CS.
So do you have, did you, I mean, are you convinced that this is the Kruskal's algorithm?
Yes, sir. Yes, sir.
Okay. What is the runtime? If I ask you to compute the runtime of this algorithm, how will you do it? Come on, Kuntal, say something.
Yes, sir. We are,
You don't have to tell me in one thought.
first,
How are you thinking?
first we are just sorting the edges.
Yes.
So if there are E edges, so
Hmm.
we have to sort them.
Right.
Oh.
So you have to sort them in this line. How much time
Yes.
does it take?
For sorting, we have to take, if there are E edges, then E log E.
Very good. E log E is the time taken to sort them. Okay.
Yes. And then for then we have to start from the minimum weight edges, then minimum weight edges, and then we have to calculate just we have to add those edges from from minimum to maximum. We have to just add the edges in the minimum spanning tree.
Okay. So how much time will it take? Just E.
E.
So you say that from this to this is take E, right?
E is.
Okay. So all total you are claiming it will be E log E plus E.
I think so.
Okay. Let me ask your friend Akshay. Akshay, are you there?
Yes, sir.
Yeah. So you are from MTech CS or MTech CRS?
I'm a JRF, sir.
Oh yeah, JRF, excellent. So can you tell me, did your friend tell the right thing?
The ordering part makes sense, and for the second part, ordered by weight, if you're adding. So we have to keep in track whether we visited the vertex before, right? So to make sure that we are not forming a cycle.
What do you mean by visited a vertex?
So basically, if a cycle is formed, that means I already have visited the so I have already visited the vertex before, like in the thing. I just have to keep in track of which vertices I visited, right?
I don't know. So for example, say I have this graph, right?
Yes.
Okay, now I first pick this edge. So that means according to you, these two graphs are visited, right? Then I take
These two
this
edges are visited.
edge,
But yeah, vertices are visited.
these two vertices are visited.
Yes.
So then this edge, should I take it or not?
Okay.
Both of
Yeah.
the edges are visited. Both of the vertices are visited.
Yes. Yeah. That's problematic. Yeah. Yeah.
So this is visiting the edges is not a very good idea to go about it.
Okay.
Venkatesh, are you there?
Yes, sir.
Yeah. So,
So,
can you help us?
sir,
Yeah.
in this loop, actually, for every edge, we are looking for, we are comparing this edge with
Correct.
all the elements of A. Because if it is forming a cycle with the edges of A or not.
Yes.
So, so in every step, we will have one edge. If it is a ith step, then we will have I edges in A.
Yes. Yes. That's true.
So it will take I inside. I am not getting correctly, but it will take.
Okay. So first of all, one thing is that as your friend has told initially that the first one takes E log, no doubt.
Yes, sir.
Right. Now you have a for loop, meaning this whole thing happens for, it can in the worst case go for all the edges in E, right? So if I want to do it carefully, let's see first. Firstly, it will be the time for sorting. This is order E log E. E size of E, log size of E. Then there is the for loop, right? So the for loop is done order E times. Now this is fine. For E times is ordered start. But then inside this, what this pseudocode is saying is that check if the by adding this edge you create a cycle or not. How will you do that? How will you check whether an edge, by adding an edge, a cycle is formed or not?
Sir, we can just keep a track which vertices were visited. Like if
I just gave an example right here. So things are visited is not a very good option.
So we can, hello, sir, am I audible?
Yeah, yeah, yeah.
So we can, we suppose we select a edge UV, and we have in some sense even a disconnected graph stored in A, right?
Right. Yes.
So we can check whether BFS are connected with the edges in A. So basically, if we consider
right, that is
disconnected subgraph to A to be a DCI already connected.
Right.
That is a linear time check.
So we can check, for example, if I want to check whether by adding this edge, I will get a cycle or not, I will check in the A, which is basically the set of red edges, is U and V, is there a path from U and V? That doesn't, of course, this edge is not yet picked up, this edge is not yet picked up. But in the A, in the red edges, is there a path from U to V? If there exists a path from U to V, then I know that I cannot take that edge, then I will create a cycle. And if there is no path from U to V, then I can add a edge because it doesn't form a cycle. So how do you check whether there is a path from U to V? You use one of these BFS or DFS techniques. So although it is not written here in the pseudocode, but this is something that is here, that if adding A does it create this edge or not? The first and most simple implementation is using DFS and BFS, or DFS or BFS, whichever it is. So every time you go over U and V, you check whether by adding this age create a cycle or not. So within a for loop, this thing can take up to order V plus E number of steps. You can do a little bit of other calculation, but that will not help you. Hello, am I audible? Hello, am I audible?
Yes, sir.
Yes, sir.
Because sometimes I get this weak signal information and I don't know how to. So in each loop, okay, inside each loop, or for each iteration of the loop, you can think of, I need order V plus E to check if there exists a path from U to V. And this is using BFS or DFS. So the time complexity therefore becomes this, which is order E log E plus order. Now see, this is a loop, right? So within each loop, you have this thing V times this statement, right? V plus E. So which is basically assuming that V is less than E, this basically becomes order E square. Okay, is this clear?
Sir, the keeping track of the vertex will work in the Prim's algorithm, right? Because we only have one connected pin.
No, I have not gone to the Prim's algorithm yet. Let's do the Kruskal's first.
Okay.
Okay. Is this Kruskal's algorithm running time clear?
Yes, sir, it's clear.
Okay. Now, let me tell you a very important. So, if I just let me tell you an important thing here. Okay. So, something that you guys kind of pointed to earlier, but did not actually end up being able to formulate it correctly. Okay. Now, whatever I'm going to say now, this is a bit more tricky. So, basically, when I want to check if by adding this age, a cycle will be formed or not. In some sense, what I'm asking is that consider this graph, this vertex, and look at in the red edges all the vertices that are connected to it. Right? So what is the connected component of U? And look at what is the connected component of V. Are these two connected components same or not? Right? So if the connected components are same, then we are done. Then we know that we cannot, that means we cannot put an edge. If the connected components are different, then we know that I can add an edge. Say we have that, I have somehow have understood that this is the connected component. So U possibly ends up storing the connected component of U. Okay, so every vertex has connected component of U. It's a set of all edges that are connected to U in the red edges. Okay, similarly here also CC of V is connected component of V, and CC of whatever, say U prime, says U prime, this is V prime. Right now, if say these two connected components are different, that means if say CCU and CCV are disjoint, distinct, disjoint, that means U and V doesn't have the same connected component. Then I can of course add this edge. Great, I will add this edge. But then what happens? If I add this edge, what happens to the connected component of U? Can you say what happens to the connected component of U?
Sir, I don't get the question properly.
You don't get the question properly. Okay. So you understand what is the connected component of U?
Yes, that I understand.
Okay. So this is the tree at this point. Okay, the graph at this point. Okay. So the connected component of U. So this is, by the way, in A. Okay, you realize that. So A is the set of all edges that we have picked up. And not in G. Okay. Now, if connected, so say connected component of U and connected component of V are distinct or different, then can I add the edge UV?
Yes, yes, surely.
Okay, I can add the edge, right? Why?
Okay.
Because they are not in the same connected component. So by adding it, I will not create a cycle.
Yeah.
Okay, now I added that. So in A, I have added this red edge here. I've added this edge UV. In that case, what can we say about the connected component of U? So right now, A has become A is equals to A union UV. What happens to the connected component of U?
Sir, U now becomes a part of connected component of P. It's a common connected component now.
So that means connected component of U would be
the both together become a single connected component.
Yes, together they become a single connected component, right? The connected component of U has to be unified in some sense. So all the edges that could be reached from U and all the edges that or the vertices that could be reached from V, you can reach this whole set from U only or from V only, right? So that means connected component of U is becomes connected component of U plus connected component of V. And that's good idea. But except that you have to change it for everywhere, right? You have to go and change it for all the possible vertices in the connected component. If connected component of U prime has also changed, connected component of V prime has also changed. So this is one way of keeping track of whether I am going to add a cycle or not by adding a vertex or by adding an edge, is to maintain the connected component of every vertex. And then we have to somehow update it as and when the algorithm moves on. Now, this is not trivial, okay, as I told you. So what I can say is that, yes, the runtime, the basic implementation that we have talked about just now, some time ago with the DFS and BFS would give you this basic implementation of the algorithm. But if you use a new data structure, I'm not explaining the data structure. If you are interested in, you guys can look at it. The data structure is called union find data structure. This data structure does exactly as what I just now told you. It maintains the connected component of every vertex. Okay, and if you do that, then you can, instead of this whole thing in done in order E times V plus E, you can end up doing it in ordered E steps. Very simple, right? So that means, in other words, you would be able to do this whole thing. The ordered U is this is an ordered E steps on, and so you will be able to do this whole thing in just order one step. Okay, by storing some extra information. Now, again, this is not be a part of this exam. I am not going to ask you any questions from Union Find, but for people who are interested in it, that is what I'm talking about. That if you So there are data structures, which means that if you store the right thing at right place, then that might help you to do this whole thing in order one step. And one such thing that helps you do it is the what is called the union find data structure. And that would basically imply that the total runtime of the Kruskal's algorithm would be order E log. So basic implementation gives you order E square because of this thing of DFS and BFS every time you do a for the for loop. But if you have some other clever union find algorithm data structures, then you will be able to do it in much smaller time. Okay.
Hello, sir.
So
Hello.
yeah, go ahead.
So just
Yeah,
asking, like, we do not know about the union find, but whether this usage increases space complexity or it keeps the same space complexity and improves the time bound.
It does include this space complexity a little bit. Yes,
Okay.
You have to maintain a separate space thing. Actually, there might be some space saving data structures also, but I think the basic structure of union find data structure uses another space. Yeah.
Okay.
Okay. Okay, good. Now, any questions on this thing so far? Okay, so if not, you know what's coming next, right? So we have the Prim's algorithm that you guys have seen in the last class, right? Hello, can you hear me?
Yes,
hello.
sir, you are audible.
Yeah. So here we keep on. We start from a small set of. We start from a vertex, and kind of slowly grow the tree, right? At any point of time, we have a tree, a subtree of the graph, and we look at all the edges that going out of that tree, right? And we pick the edge which is the smallest among them all, and we continue like that. So that's the Prim's algorithm. So I don't want to go into this. Yeah, we have seen this example in the last class only, so I don't want to go about it. So here is this, the pseudocode. So U is the set of all vertices that are the vertices that we have touched so far, right? So we start with a vertex, and without loss of generality, we can start from the vertex 1. And while we have not touched every possible vertex, what we do, we look at the edge, which is the smallest weight cost edge, such that the vertex is in U, and the U is, one side is in capital U and the other vertex is out of capital U, right? And if by adding that vertex you don't create a cycle, then you add it to the tree and go ahead. Okay. Now here, any questions about this particular algorithm? Is the algorithm clear, first of all?
Yes, sir.
Okay. In that case, what is the runtime of this algorithm? See, there are, as you can see in the Kruskal's algorithm, you can have a basic algorithm, right? Which might not be very efficient, but at least you have something. And then you can you can see whether using a particular data structure or something that can be done. But first tell me what is the basic runtime algorithm, the basic algorithm. Who can tell me now? Let's see.
Sir, it should be V plus E.
Okay, why?
Sir, it's just like it's just like BFS type of thing. Like not exactly BFS, but we are just traversing through every vertex first, every neighbor first, and then we are selecting the lowest edge. So I'm not considering the cycle check, but apart from
Yeah,
that,
but
it
what
should
is
be
the cycle check? That's the most important. Like if you remember the last time, cycle check was the one that was killed us.
Here the cycle check would not be like essentially the thing is that if the one of the edges in like G does not belong to you, then obviously the cycle would not form, because essentially the difference from pre-crystal here is that it is always maintains a connected
Yes, so
component.
V doesn't
It's
belong to you, then
never
it will not be there. Right, that is very true.
So and we have to check that V does not belong to you. So given that we do not have any kind of ordering of the vertex,
Yeah.
so to say, it I think can be you. So that could be order of G operations essentially, I think.
Okay. So what will you do? We'll just keep on checking whether V doesn't belong to you, right?
Yes,
We'll
for each
check.
step there is
we
a
can
linear
just maintain a
guide.
Boolean array for that, sir.
You can maintain a Boolean array, and
It will just directly check whether it belongs to you or not. If we are visiting it once, then
so
we'll
basically,
make it true.
yes. I mean, so whenever we have this, when an edge comes, so for every vertex, we can maintain, for every vertex U, we can maintain, say, a mark of U. So that means these are the mark, meaning that vertex is in U or not. Right. And now what I do is that as soon as I get an UV, okay, among the I can go over all the vertex edges one by one. Right? I can go over all the vertices one by one, and all the edges from lowest to smallest kind of. So this is another thing. How do you go over all the edges?
Sir, we can sort them.
Okay, but you are not going over all the edges in one go, right? You are only going over those edges such that one of them is in U. So you see what I am saying? So you cannot, like, you don't have a, you don't want to, first of all, if you do sorting, then that will take some time possibly. But if you don't sort them, I mean also if you do have a sorting thing also, say even after that, so this is the lowest cost edge such that, I mean, yes, you told me to check whether both of them are not in U, but you have to ensure that one of them is in U. Right? Because maybe this whole will take order E steps every time. Fine. How will you do it?
Sir, your voice was breaking in the last part. Before you said how you do it, it's like the last part after that.
So how are we storing this? This is an adjacency matrix or a adjacency list. How are we storing the graph?
Adjacency list. Adjacency list. We have an adjacency list. No, so what I was saying is that see, you told me how to ensure that I am by checking that not both the endpoints of the vertex that I'm planning to add is in U. So that I can check. If U is marked, right? If all the edges that we have, vertices that we have touched, they are marked, right? Which is very simple. I can mark it using another array or something. Or in that case, I can check that an edge I will not create a cycle. That I completely agree. But how are you going to find out the lowest cost edge among those edges that have at least one vertex in U? Is this problem clear? Where the issue is coming? Hello.
Hello, sir.
Yeah.
You are audible. Yes.
Yeah, sorry.
You are audible. The question
Yeah,
was
so
clear.
the problem is clear.
Lowest cost edges, we have to look for all the marked vertices and their next neighbors.
Very good. That's all that we have to do.
So we have to keep track of this all marked vertices, and then we have to look for which is having lowest cost edge from that marked vertices.
Correct. But that would take some time, no? Okay, so maybe I should just
Sir, can we pre-process everything? Like
you can pre-process, but what will you pre-process? What will you store after processing?
we can just like maintain some stack or something like that, and we can just start removing the lowest edge, the vertices of that lowest edges. No, it won't work.
That would be
Okay, so for maybe we should take it a bit slow. Okay, for people who are going up, maybe are possibly struggling a bit to understand what exactly is going on, let's try to first see a very simple thing. Okay, one thing that we can do is that we can see, as soon as I have this is my graph that we have created till now. Okay, and then there are other edges that are not connected, right? As soon as, so I will try to, one option that is possible is that look at all the edges, look at all the edges that are going out of U. Okay, maybe even including this kind of stuff. These edges I can create a min heap kind of stuff, right? And the min heap, I will find the lowest edge weight. If it is this, I will check whether this creates a cycle or not. That I can check in order one time because I have a marking. If not, then I will remove it, right? I will basically say, oh, okay, so this edge is gone, so I'm not interested in this. Now, among the new edges in the min heap, I'll find the next minimum. So maybe this one. So I will add this edge, I'll add this vertex, and now all the edges that are going out of the newly added vertex, namely this one, I will put it in the heap, min heap. So at any point of time, therefore, I am maintaining the minimum min heap of all the edges that are having at least one edge points in the vertex, in the U. Okay.
Sir, why at least? We can take exactly one.
You can take exactly one also, right? How?
Yeah.
So in that case, I
Because
should
it-
remove it. See, there are two parts, right? So I have added this one. So consider the time when I've just added this edge. At this time, I should add this edge in the min heap. And if you want to kind of not do any worry about it, about throwing the edges, then you should remove this edge. Now, problem is that this edge removing, this is not necessarily in the top of the mean heap and all those things, right?
Okay. Okay, I got it.
So it can be done. It's not unreasonable to do it, but one simple thing is that it doesn't help us such, so we can leave it with doing a I mean, just adding this new edge in that. Maybe some other edges are still part of them, like this edge and all. But whenever this do come up in the picture, they will be removed because it will not create a cycle. It will create a cycle. Right. So that means at any point of time, I have to maintain a min heap kind of a state. Now, if you think about it, how much time will it take for the min heap to work out? So I have to add this edge, right? Add this edge to the min heap, which possibly has something like ordered E number of edges already sitting there. So in a min heap, if you remember, by adding an edge, it can take up to log n number of things, right? Right? Some log n times, right? So how much time will it take here? So in that case, we can just do this whole thing, and this will take every time I'm adding one vertex, right? But I might have to go over all the edges that is there. Right? So it will be, sorry, every time I will be doing an every time this while loop, right? How long will the while loop take? The while loop will take order v times v number of loops that will be there, and every time I would be going and picking some set of edges and I will removing them or adding them, and that will take order how much? E log E kind of time. Sorry, yeah.
It should be just log E, right?
E kind
We are adding only one edge to the heap, or we are adding.
Are we adding only one edge? Think of it. Are we adding only one edge?
Yes.
How many edges are we adding?
All the edges that are possibly emerging from the new vertex that we added.
So
which
sir,
is? I had one question regarding this.
Yeah.
So essentially,
what
we
go ahead.
discussed in the earlier section that when we are adding a new edge, we are removing that edge from the adjacent list. Suppose in the new vertex that is added at the bottom left, it has another edge that has been already added to the heap, right? The one going to the top.
Right.
So we cannot essentially know that that vertex has been added if we are not updating the adjacency list accordingly. So are we also doing that, or are we adding multiple instances of edges in the heap? Like how are we getting around
that?
Add
multiple instances of the edges, so that's not a big deal. But that will only be done twice, right? Once for this one and once for this one.
But are we doing that? Like we cannot.
Every edge will be added at most.
Added already, right? Okay.
Yeah, you can do. See, I mean, you can do it. Like, one thing you can do is that you can look at all its neighbors. When you add this, once you know all its neighbors, then if you find it's one of its neighbors has already is in U, then you can remove from the heap. So this is something that I have not told you how to do it, but there is an operation that you can do with the heap in which you can remove a particular node from the heap. Okay, so this edge possibly was sitting inside the heap somewhere, right? That is not necessarily in the top, but somewhere in the middle. You can remove this vertex edge from the heap. Just think about it, you can do it actually. The same way as we do the extract mean kind of stuff. Okay, slight changes to that. So you can do that, or you can just leave it there. I mean, that will have twice. I mean, every edge will be added to the heap at most twice, and which is we will face it, and we have to. But it doesn't matter. Both of them will have the same time complexity, because removing a vertex or edge from the heap also takes log e number of steps. And if you see, if this edge at some point of time comes up as the mean heap, as the topmost of the mean heap, right, as the minimum, then also you kind of want to remove it and discard it, and that will also take order e steps.
Okay.
Right.
Okay. No, sir. I think when we were discussing DFS, these things, there was another like in something traversing. We are discussing that when we are visiting a edge, we are essentially discarding that from the edge list or neighborhood list of the.
Oh, so you want to do that? That also you can do. That
Yes,
also
yes,
you can do.
We can
Yes,
also
that
remove
also
that
you
from
can
the
do. When you are
definition
saying that,
no, I
you
am
can also remove
removing
it from the definition, from the tree itself.
Yes, yes.
From the graph itself. Yes, you can also
Yes,
do
sir,
that.
yes,
That also will avoid adding twice. Yeah.
Okay. Okay. Yeah.
But yeah. So, but the important thing is that for as soon as I'm adding an edge, how much time I am taking? Can you just let's calculate it? When I'm adding a new edge, how much time does it take? It can take at most the number of degree of it, right? So degree of I into log e number of steps, which is v log e. I mean, less than. So that means every operation now here will take v log e number of steps. Okay. So since this whole thing, right? And actually speaking,
hello.
Yeah.
So we can argue that it essentially cannot take more than v log v. Oh no. Okay. Yes. So I was thinking that we are only storing the edges in a tree and then we can reduce the log e to log v, but that is not the case.
Right. Yeah. So you can do this thing also, which would be 2 times or order of e log e. This whole thing can be therefore brought down to e log e. So one thing is that you can say that, okay, see, there is a while loop, and inside this while loop you have v number of times, and inside each of them you are taking v log e number of steps. So in that case, so maybe I should have not in this particular part here. Our time complexity is order v times v log e, so there will be v squared log e number of steps. So while loop for v times, and in each time I am going to only take v log e number of steps. Okay. You can do something more. In fact, you can do such that, okay, not all while loops are taking the same amount of time. When I'm the while loop in which I'm adding the ith vertex, I am taking di log I number of steps. So which means that I should take order of e log e number of steps. Now e log e is slightly better than v square log e. Same pseudocode. We are analyzing it in slightly more sophisticated way. and I can get down to E log E number of steps. Now there are other things that you can still do. Okay, and I don't want to really go into these things that much. I mean, I have already gone into this heap kind of stuff, which was not what I was intending. So think about it very carefully. I mean, think of it at home also. This Prim's algorithm, if somebody asks you to come up with a time complexity for this, it is important that you give an upper bound. Okay, and the upper bound better be correct, meaning you have to do all these steps correctly. Now, there is a much more simpler upper bound of order V times E or something like that. So which is basically V cube. If you want to do it a bit more cleverly using heaps, as we just now explained, you can do it to order V squared log E, or even up to V log E. So let me see. I don't want to do this proof. Yes, you can do. I mean okay. So I have this E log E, and I can have an even cleverer algorithm of order V square. I have not done that in the class. Okay, but think about it. Okay, so basically this algorithm, I have produced you V square log E, I have produced you E log E, and there exists an algorithm or the implementation that can be done in order V square, and that is quite nice. Okay, but actually, if there is some more data structure that you can use, which is called the Fibonacci heap data structure, and again, this is something that I will not be doing it in the class, where you can do this implementation even further, and you can get it down to order E plus V log V. So this is not linear time because there's a V log V part, but you can push. So you can think of this one. Okay, this one you can take it as an exercise if you want. Okay, try to come up with an implementation that will give you order V square. Okay, this is actually not hard. Think about it. I mean, we will be doing this order V squared algorithm sometime after the midsem on a different problem. We will see the similar implementation of such a thing. If you guys are familiar with algorithms, I can say if you have seen Dijkstra's algorithm implemented, so this is, you can use this same technique to get order V square. So this is similar to Dijkstra. But if you are not familiar with Dijkstra's algorithm, no problem. We will come back to it later. So the most basic algorithm is, say, so we can talk about with the heaps V square log E. We can do slightly better E log E. You can do order V square, and using Fibonacci heaps, you can push it down to order E plus V log V. This is the best that you can push it down to. But again, this uses this concept of Fibonacci heaps. Just like in the case of Kruskal's, I kind of did not go into union find. Here also, I'm not going to go into Fibonacci heaps, but I'll let you guys, if you are interested, you can go and study it for yourselves. It's a data structure, separate data structure. And using that, you can push it down to E plus V log V. Okay. So that is basically the various these two algorithms that we have for MST kind of stuff. Once again, for whoever is present here, I will tell you, please go back and read the algorithms try to understand, try to prove the correctness of the algorithm, something that is not at all obvious. These algorithms are not like the sorting algorithms where the correctness is trivial. So you have to prove it. And also, as we discussed today, try to find the time complexity of the algorithm. As you have seen, many times this algorithm's time complexity depends upon how you are implementing the finer details. Certain things you can say when we define algorithms, we say, oh, do these things, check this thing, and done. But the actual, all these simple operations that we are supposed to do, simple checks that we are supposed to do, they add up. And that's where implementing those checks cleverly using less runtime is a part of this designing a good algorithm. Okay, so any questions other than whatever has been done? If you have, if you have any questions, please let me know. I think I'm really running short of time.
Sir, one question regarding the maze stem.
Yeah.
Will there be like the past problem sheet that we received was quite heavy on recursion and like recursion things? So will there be questions like that in the maze stem? Okay.
So recursions, there will be some questions possibly from for finding out solving recursions and all those things. Okay, but not too many. So if not, but there will be algorithms where you will be kind of guided in some sense to design recursive algorithms, and then you will be asked to find the running time.
That is okay. Like the closed form for recursion calculation that was given in the first assignment. Yeah. So I was talking about that. Okay.
So that. So I am not in town today. I am actually outside, but I will be back tonight. So before, so when is the end sem by the way, mid sem by the way? Which day?
It's on Wednesday, I guess.
6th, I think.
On Wednesday, right? So if you guys want, I will be there from tomorrow, day after tomorrow, or Monday, Tuesday, whichever time. So if you guys want to discuss some doubts, clarify doubts, I will be available in my office, mostly from say 11 to 5 or something like that. So please stop by anytime. Don't be shy. And if required, I will be happy to take. I mean, if you some few of you comes with some doubts, I'll be happy to take some extra whatever tutorial kind of classes.
Sir, the question you
offline,
started in the start of this class.
Yes.
Can it be possible to have two MSTs generated by Prim's algorithm and algorithm?
Yeah.
I think we haven't found the answer, right?
We have not found the answer. So I just kind of guided you in that. Okay. I think so.
One more thing, I have this question also, because every MST can be generated by these algorithms.
Yes,
if it is that,
then you can generate every MST by these algorithms.
So if it is that, then we can find if order is not the matter, right? So we can take any order.
Yes, but how do you prove that? So that's the first thing, that anything is produced by the MST, right? So that's the main idea, right? I mean, you have to prove the fact that, I mean, it is true, but you have to prove it, that any MST can be produced by Prims or any MST can be produced by Kruskals. Okay, and that is why I left you with that particular problem, that you think about it, that an MST, so all the MSTs will have the same frequency of weights. Okay.
Here, same frequency of weight means
number of edges of weight 1 will be same.
Yeah. They
Number
are
of
same.
edges with weight 2 will will be same. Okay, any MST, irrespective of what algorithm is it used to find it, will have the same frequency of edge weights. Okay, from that you can kind of easily prove that Kruskal's algorithm will produce all the, or can produce all or any of the MST depending on the ordering of the edge weights.
Hello, sir.
Yeah.
Sir, partition of some number into n-1 parts, it is unique.
Partition of some number into n-1 parts.
Yes, sir. Since tree has n-1 edges, so we are summing n-1 weights.
Right.
And from any algorithm, we are getting minimal spanning tree. So some of the edges of minimal spanning tree, it will be same.
Sorry. You are trying to, I mean, from that our problem, you are trying to say some statement on that direction, right? That is okay. I understand what you're trying to say, but that is, you have to be a bit more careful. What do you mean by partition of number in -1 thing?
Actually, suppose 10 is a number and partitioning of 10 into n-.
What is n?
N is the number of vertices.
So what do you mean partition of number? Partition of number, so 10, n, there's a lot of things which are not, I mean, how is 10 related to n?
Sir, I will mail you.
Okay, sure. Yeah,
So, sir, I can think of a proof by contradiction here.
Proof by contradiction of what?
The statement for the frequency statement.
Yes.
So essentially, suppose we say that k is the first number where the frequency is different.
Right.
And we say that with the loss of energy, one of them has lesser of k.
Right.
And so if the other, like, I would take some time to formalize it, but if the other one has some less k, it has to be supplemented to make those the sum of the weights same at some higher like some value greater than k, and then there the reduction would occur. The number of elements cannot be the same if it is replaced by some higher order edge, like higher number than k. So from there you can derive a contradiction.
Yes. I mean, basically the same thing that you did for the unique setting.
Yes.
Yes. Similar argument for the unique setting.
Sir, mid-sem syllabus.
Anything that we have done till now. Mid-sem syllabus is anything that we have done till now.
What is the marks partition? Is it 30 or 40?
Usually I put 30 in mid-sem.
Yes, sir.
Yeah. That's what I usually put.
Sir, exam will be in 30 marks only. It will not be scaled.
No, it will be some. Oh, okay. So this is another thing that I should tell you guys. So usually my questions are on, say, 120 marks or 130 marks or something like that. Okay. But you will have to solve at most 100, or basically you can solve anything that you want. Okay. The marks that you will get is minimum of your score and 100. So that means if you score less than 100, you will get your score. That is your score out of 100. And if you score 120, you will get 100 only out of 100. Okay, so there will be something.
Sir,
like,
what will be the duration?
It will be around 3 hours or 3 hours, I think. Okay.
Sir, will there be any proof of correctness?
Yes, of course. What do you mean? I mean,
okay.
By the way, whenever I say that design an algorithm, okay, I will leave it to you to understand. Design an algorithm, and even if I don't say it, you are supposed to give me a proof of correctness and analysis of this till runtime, even if I don't say it.
space and time also is needed, right, sir?
Time is required, space is fine. Unless I ask you, don't worry about space. But at least time, you should do it. Okay, because space, we have not focused on space that much, because space is something that is a bit more ugly in that respect. Yeah, I will try to be very accurate when I write the questions, but I might someplace forget it. Oh, and also there will be questions like this one, okay? Design an efficient algorithm. Now, what does that mean? It means that most likely it will mean that there exists a trivial algorithm, okay, that has some runtime. Okay, you can give me that trivial algorithm, prove the correctness, and give me a proof of estimate of the runtime and all those things. But that doesn't mean that you will get full marks, because there might be some algorithms that are even, I mean, I was expecting something faster. So this I will be a bit vague about it, and that you have to kind of understand what is the right thing. So it will not be too complicated, but maybe I'll tell you that an algorithm in which you can apply DFS and get a linear time algorithm, but you have applied sorting and done something and you have obtained a E-log number algorithm. So the person who gives the E-log algorithm is also correct. You will get some marks, but not necessarily full marks. And the person who has given the more efficient algorithm will get the full marks. Okay, so when
sir,
yeah.
In that case, we don't have to show that it is efficient, right? That does not we have.
No, just you have to somehow convince yourself that okay, with the tools and all that I've learned and all those things, I think I can do this thing better. Okay, you don't have to show that this is the best. No.
Okay, sir.
Sir.
Yeah.
Sir, if you ask for say order of n algorithm,
yes,
and I am unable to get that, but I can give you a order of n square algorithm, then will I get any marks?
Okay, see, it's hard to say, but if I have asked you an order of n algorithm, and if you get order of n square, you might get some marks, but clearly it will be not much, right? Because when I'm saying an order of n algorithm, then that would mean that I'm looking for an order of n algorithm. I expect you to do it. But if I say that, okay, give me an efficient algorithm, and that you give me an order of n square algorithm, although there exists a simple order of n algorithm, then you will get maybe 60% of the marks or something like that. Okay, I think
okay,
yeah, stop here. If you want to have discussion, you can come to my office tomorrow, anytime, or day after tomorrow. The only tip I can say is that try not to memorize the algorithm. It will not take you anywhere. Try to understand the algorithms, the proof of it, and the how to compute the running time. Okay, and try out as many problems as you can. I've given you problem set. Try out for problems from the problem set. There are books. Try them out. I mean, I know that studying in the 12th hour is not a very great idea, but I mean, with whatever time you have, try to do that. Okay. Okay, I think I will stop here today. And if you have any questions, doubts, either drop me an email or just come to my office directly. So see you in the mid-sem class. Okay, bye.